Good morning all. Welcome you to the fourth part of the chapter Relations and Functions. In the last class, we discussed first 6 problems of the session Relation. Today, we are continuing the problem section. We are going to do problems from 7 to 10. As I mentioned earlier, there is no separate note in problem section. First, see the question, write it down in your notebook. After listening my explanation, you have to write the answer also to your notebook, just like as in the screen. Let us see question number 7. This is question number 7. Very beautiful and important question. The peculiarity of this question is this question involves all the concepts which we have discussed today: equivalence relation, equivalence class, and partition. The question is this: RB, the relation on A is equals to 1, 2, 3, 4, 5 defined by R equal to ordered pair AB such that mod A minus B is even. The relation is defined on this finite set, and this is the relation. For AB to be a member of this relation, the difference between A and B must be even. That is the condition. We want to show this relation is an equivalence relation. For that, first, we want to show that the relation is reflexive. Okay. When we say that a relation is reflexive, the relation must contain AA for every A in capital A. That is 1, 1, 2, 2, 3, 3, 4, 4 and 5, 5 belongs to this relation. In general, we can say AA belongs to R for every A in this set. For AB be a member of this relation, mod A minus B is even. Then what is the condition for AA to be a member of this relation? Mod A minus A is even. What is mod A minus A? Mod A minus A is mod 0. Mod 0 is equal to 0. Is 0 an even number? Sure, 0 is an even number. Therefore, mod A minus A equals 0. 0 is an even number. That is true for every element in this set A. Therefore, the relation is what? Reflexive. Some students may confuse that. What is the reason behind 0 is a real number? The answer is that to be an even number, the number must be of the form 2n. We can write 0 as 2 into 0. We can write 0 as 2 into 0, that is of the form 2n, therefore 0 is an even number. Then some may say that we can write 0 in the form 3 into 0 also. Then it is an odd number? No, because an odd number is a number of the form 2n plus 1. We can't write 0 in the form 2n plus 1, and hence 0 is not an odd number. Clear? 0 is an even number, not an odd number. For the reason is that we can write 0 in the form 2n, we cannot write 0 in the form 2n plus 1. Now come back. Mod A minus A equals 0, it means that AA belongs to R, hence the relation is what? Reflexive. Mod A minus B is even, the relation is reflexive. Now let us discuss symmetry. To be the relation is symmetric, whenever AB belongs to R, then BA must belongs to R. Suppose AB belongs to R. What is the meaning of AB belongs to R? Mod A minus B is even. Mod A minus B and mod B minus A are same. Therefore, we can write mod A minus B is even implies mod B minus A is even. When mod B minus A is even, clearly BA belongs to R. BA belongs to R. Whenever AB belongs to R, then BA also belongs to R. Hence, the relation is symmetric. Now, let us discuss the transitivity. What is the condition for transitivity? Whenever AB belongs to R, BC belongs to R, AC must belongs to R. Suppose AB belongs to R and BC belongs to R. What is the meaning of AB belongs to R? Mod A minus B is even. What is the meaning of BC belongs to R? Mod B minus C is even. Together we can say mod A minus B and mod B minus C are even. For A minus B, mod A minus B is even. A minus B, the number A minus B must be even. Similarly, the number B minus C must be even. A minus B is even, B minus C is even. Okay, then its sum is again even. That is, A minus B plus B minus C is even. That is the next step. A minus B plus B minus C is even. Minus B plus B got cancelled. What is the answer next? Then mod A minus C is even. Since A minus C is even, its magnitude, its absolute value is also even. That implies mod A minus C is even. When mod A minus B is even, AB belongs to R. Hence, when mod A minus C is even, ordered pair AC belongs to R. Okay? Ordered pair AC belongs to R. It means that whenever AB belongs to R, BC belongs to R, then AC also belongs to R. That is the condition for transitivity. Hence, the relation is transitive. Then, this relation R is reflexive, symmetric and transitive. That are the three conditions for an equivalence relation. Hence, the relation is an equivalence relation. Okay. The same question can be asked in different ways. That is, mod A minus B is even. Instead of that, the same question may become like this: mod A minus B is a multiple of 2, or mod A minus B is divisible by 2, or A minus B is even, or A minus B is a multiple of 2. All questions have the same answer. Okay, now write it down to your notebook. Now let us discuss answer to question number B. What is class 1 and class 2? What is equivalence class of 1? Equivalence class containing 1. The set of all elements related to 1. How many elements are there in this set? 5 elements. Which elements are relating to 1 in this set under this relation? For to be a member of this class, that element must be related to 1. Okay, equivalence class containing 1, that element must be related to 1. Is 1 related to 1? Sure, 1 minus 1 is even. Therefore, 1 is a member of this set. What about 2? What is 1 minus 2? Is 1 minus 2 even? No, 1 minus 2 equal minus 1, it is not even. What about 1 minus 3? 1 minus 3 is equal to minus 2, it is even. Hence, 3 is related to 1. Similarly, 4 is not related to 1 and 5 is related to 1. What is the reason? Difference of any two odd numbers is even. Difference of any two odd numbers is even. And difference of an odd number with an even number is not even. Hence, the set of all elements related to 1 are the odd numbers in this set, which are the 1, 3 and 5. Therefore, equivalence class containing 1 equals set 1, 3, 5. We can say equivalence class of 2 in the same way. The difference of any two even numbers is even. Therefore, the set of all even numbers in this set contain the equivalence class 2, which are the set 2 and 4. Then class 1 equals set 1, 3, 5 and class 2 equals set 2, 4. Then what is the last question? Question C. Show that class 1 and class 2 form a partition on A. How many conditions are there for a partition? 3 conditions. What was the third condition? Third condition is more simpler to say. Therefore, I say that condition as the first one. That is, the union is equal to A. Union of these two sets equal to A and intersection equal to 5. We want to show that these two sets form a partition of this set. Okay. For that, first we are going to prove that the union of these two sets is equal to A. What is the union? 1, 2, 3, 4, 5. Class 1 union class 2 is equal to class 1 union class 2 equals to 1, 2, 3, 4, 5. That is equal to A. That is union equal to A. What about the intersection? Is there any element common? No, there is no common elements. Therefore, intersection equal 5. Class 1 intersection class 2 is an empty set. Therefore, one condition is over. What about next? C. This set contains 3 elements, 1, 3, 5. Every elements are related to each other. Every two ordered pair belongs to the relation. 1, 3, 3, 5, 1, 5, 5, 3, etc. belongs to the relation, because the difference of any two numbers in this set is even. Therefore, every element in set 1 are related to each other. In the same way, every element in this set 2, 4 also related to each other. That is the second condition. Every element of class 1 and class 2 are related to each other. And what about this? Whether the element 1, 2 belongs to R? Is difference of 1 and 2 is even? No. 1, 2, 1, 4, 3, 2, 5, 4, 4, 1 are not an element of their relation. It means that no element of class 1 is related to any element of class 2. That is the third condition. No element of class 1 is related to any element of class 2. These are the three conditions to be a partition of a set. These three conditions are satisfied by these two sets. Okay, therefore these two sets, that is class 1 and class 2, form a partition of A. Answer to question number C is also over. This is a very beautiful and important question. Study it well, write it down in your notebook beautifully. And let us discuss question number 8. This relation is a relation on geometry. The relation is defined on the set L. L be the set of all lines, and two popular relations on the set of all lines is perpendicular and parallel, perpendicularity and parallelism. First, we are going to discuss the relation perpendicularity among the straight lines, and next we are going to discuss parallelism. We are going to discuss the reflexivity, symmetry and transitivity of these two relations, perpendicular and parallel. What is question number A? There are two relations, R1 and R2. R1 is the relation perpendicular and R2 is the relation parallel. We are going to show in as answer to question number A that the relation perpendicular is symmetric. What is the condition to be perpendicular? L1, L2 belongs to R1. R1 implies L1, L2 are two lines. L1 and L2 are two lines, two members in L, set of lines. L1, L2 belongs to R1 means L1 is perpendicular to L2. We want to show that L2 is also perpendicular to L1. For that, we are going to draw its picture. Okay, L1, this is line. L2 is perpendicular to L1. Therefore, we can draw L2 like this. L2 is perpendicular to L1. Here, L1 is perpendicular to L2. Very clear. L2 is also perpendicular to L1. L2 is perpendicular to L1. Whenever L1 perpendicular to L2, L2 is perpendicular to L1. When L2 is perpendicular to L1, L2 L1 belongs to R1. L2 L1 belongs to R1. Whenever L1 L2 belongs to R1, then L2 L1 is also belongs to R1. That is the condition for symmetry. Hence, the relation is symmetric. Clear? The relation perpendicularity among the lines is a symmetric relation. Now, what about the reflexivity and the transitivity? Okay. This is a line L1. Is this line perpendicular to itself? Never. One line cannot be perpendicular to itself. Okay, a line cannot be perpendicular to itself. Therefore, the relation is not reflexive. Okay, the relation is not reflexive. What about the transitivity? For a relation to be transitive, we have to find two ordered pairs L1, L2 and L3 in R1, such that L1, L3 also in R1. L1, L2 in R1 means L1 is perpendicular to L2, and L2, L3 in R1 means L2 is perpendicular to L3. Okay, suppose this is L1, then how will be L2 perpendicular to L1? Okay, this is L2, and how can I draw L3 that is perpendicular to L2 like this? Okay, now see the relation between L1 and L2. What is the relation connecting L1 and L2? Are they perpendicular? No, they are parallel. L1 is parallel to L3. L1 is parallel to L3. It means that L1 is not perpendicular to L3. To be a relation in R1, to be a member in R1, L1 must be perpendicular to L3. Here L1 is not perpendicular to L3. Therefore, L1, L3 is not a member of R1. Okay, hence R1 is not transitive. Keep in mind that the relation perpendicular is symmetric only, neither reflexive nor transitive. Clear? Now discuss answer to question number C. What is the question number C? The relation is changed to perpendicular to parallel. and name of the relation is R2. We want to show that the relation is an equivalence relation. To be an equivalence relation, the relation must be reflexive, symmetric, and transitive. First, we are going to show that the relation is reflexive. This is a line, and name of the line is L1. It is clear that every line is parallel to itself. The meaning is that the slope of a line is equal to slope of the same line. A line and the same line have the same slope. Parallel means slope is same. Okay. In that sense, we can say every line is parallel to itself. Hence, the relation is R2 is reflexive. The relation R2 is reflexive. Okay. What about the symmetry? To be a relation, the relation is symmetric. Whenever L1, L2 in R2, we want to show that L2, L1 is also a member of R2. L1, L2 belongs to R2 means L1 is parallel to L2. Okay. It means that this is L1. And how can I draw L2? Parallel to L1, same slope of L1. Okay, this is L2. Clearly, L1 is parallel to L2 and L2 is parallel to L1. L2 is parallel to L1. Whenever L2 parallel to L1, we can say L2, L1 in R2. L2, L1 in R2, and hence the relation R2 is symmetric also. Now discuss the transitivity. L1, L2 in R2 and L2, L3 in R2 implies L1 is parallel to L2 and L2 is parallel to L3. L1 is this, L2 is this, and L3 is this. L1 is parallel to L2, L2 is parallel to L3. Clearly, L1 is parallel to L3 also. Hence, L1 is parallel to L3. Since L1 is parallel to L3, we can say L1, L3 belongs to R2. That is the condition for transitivity. Hence, the relation is transitive also. We have proved that the relation parallelism is reflexive, symmetric, and transitive. Hence, it is an equivalence relation. Okay. Keep in mind that the relation among the lines perpendicular is symmetric, but not reflexive, not transitive. At the same time, the relation parallel among the line is an equivalence relation. That is, it is reflexive, symmetric, and transitive. One more sub question is there in C. Find the set of all elements related to the line y equal to 2s plus 4 in R2. Y equal to 2s plus 4 is a member of this set L, and we are going to find the set of all lines related to this line. It means that we are going to find the equivalence class containing y equal to 2s plus 4. Okay. For that we are going to use GeoGebra. Okay, we are seeking the help of GeoGebra. GeoGebra is a beautiful tool to study mathematics visually. Okay, to visualize mathematics, GeoGebra has an important role. So all should familiar with this software GeoGebra to make easy their mathematics study. Okay, here the line is y equal to 2s plus 4. This is line y equal to 2s plus 4. I am going to draw the line y equal to 2s plus 4. From the equation itself, we can say the slope of the line, this is of the form y equal to mx plus c, and m is the slope of the line is 2. Slope of the line is 2. And by observing the graph, we can say the slope is 2. What is slope? This angle is called inclination. Angle is called inclination. Then slope is tan theta. What is tan theta? Opposite side by adjacent side. The length of this side is 4 and the length of this side is 2. 4 by 2. What is 4 by 2? 4 by 2 equals 2. Tan theta equal 2. Therefore, slope of this line is 2. By observing the graph, we can say slope of the line is 2. By observing the equation, we can say that the slope of line is 2. And there is a tool in GeoGebra to find the slope, that is this one. Here also we can say the slope of this line is 2. M is equal to 2. 2 by 1, that is equal to 2. Okay, slope of this line is 2. Now we are going to find the set of lines relating to the given line. What is the condition for the relation? That line must be parallel to the given line. It means that slope of the new line must be equal to 2. I am going to draw such one line. Okay, this line. The slope of what is the slope of this line? 2. Why 2 by 1? 2 by 1 equal to 2, or using GeoGebra tool, we can say slope of this line is 2. Is there only one line having the condition? No, there are infinitely many lines having slope 2. I am going to draw them. Okay, these all lines have slope 2. These all lines are parallel to the given line, given right line. There are too many lines, so many lines, infinitely many lines having slope 2. These all lines are related. These all lines are related to the given red line. Okay, we can give an animation to the slider, then you can observe the fact. Okay, see the equation here. Only change, there is no change in the slope, change in only in the y-intercept. It means that equation of this all line is y equal mx plus c. C is changing, y-intercept is changing. There is no change in the slope. Therefore, equation of all this line is y equal to 2x plus c. Okay. Now we are going to write it down in your notebook. Y equal to s plus 1. We are writing. We are finding. We found that the set of all elements, the set of all lines related to the given line y equal to s plus 4 is the set of all elements related to y equal to s plus 4 is the family of line having slope 2. What is the family of lines having slope 2? Y equal to 2x plus c. 2 is the slope. Okay, y equal to s plus c. The set of all elements relating to the given line is y equal to 2s plus c. There is no change in this 2 and change the y-intercept 4 into an arbitrary constant c. I think the answer is clear to you. Now, next question, question number 9. Here the relation is defined on the set of all triangles. There are two popular relations among the set of all triangles, that is similarity and congruence. First, in this case we are discussing the relation similarity, similarity among the triangles. We are going to show that the relation similar is an equivalence relation. For that, first we want to prove that the relation similarity is reflexive. When we say that two triangles are similar, their angles are same, their shapes are same. Size may vary, shapes are same. It means that angles are same. I am going to draw a triangle that is T. Okay, clearly this triangle is similar to itself. The reason is these two triangles are same, both are T, and this triangle is similar to itself. Every triangle is similar to itself. Therefore, the relation is reflexive. Okay. Now we are going to search the symmetry. To be the relation is symmetric, whenever T1, T2 belongs to R, we want to show that T2, T1 also belongs to R. T1, T2 belongs to R implies T1 is similar to T2. It means that T2 is similar to T1. T1 is similar to T2 means T2 is similar to T1. It means that T2, T1 belongs to R, and hence the relation is symmetric. Very simple. Okay. Now discuss the transitivity. T1, T2 belongs to R, T2, T3 belongs to R implies T1 similar to T2 and T2 similar to T3. Simple. It means that T1 is similar to T2 and that T2 is similar to T3. It means that T1 is similar to T3. That is T1, T3 belongs to R. Whenever T1, T2 belongs to R, T2, T3 belongs to R, then T1, T3 also belongs to R. It means that the relation R is transitive. Therefore, the three conditions for equivalence relation is satisfied: symmetric, reflexive, and transitive. Hence, the relation similarity is an equivalence relation. The same way, we can show that the relation congruence is also an equivalence relation. The relation congruence among the triangles is also reflexive, symmetric, and transitive. Okay. Now, answer to question number B. Before that, we can just have a view on similar triangles. If you are not familiar with similar triangles, you please listen here. These are three triangles. These three triangles are similar, same shape, different size. T1 is similar to T2, then T2 is also similar to T1. T1 is similar to T3, then T3 is also similar to T1, and the remaining can be said in a very easy manner. Okay. Now, answer to question number B. There is a sub question, a very beautiful question. What is that question? I mean the right angle triangle T1 with the sides 3, 4, 5. There are three triangles T1, T2 and T3. Their sides are also given. We want to show that which are related. It means that which triangles are similar. There are three triangles T1, T2 and T3. Okay. Let us draw the triangle T1. T1, the sides of T1 are 3, 4, 5, a small triangle. And next is T2, sides are 5, 12, 13, and another one is 6, 8, 10, three triangles T1, T2 and T3. Sides of this first triangle is what? 3, 4, 5. Next is 12, 5, 13. Next is 8, 6 and 10. By observing these pictures, we can easily say which of these two triangles are similar. Is T1 similar to T2? No. Is T2 similar to T3? No. What about T1 and T3? They are similar in shape, only difference in size. Okay. Therefore, the triangle T1 is similar to T3. By observing the picture itself, we can say T1 and T3 are related. Okay. Now, we are recalling a fact which you have studied in class number 9, that is basic proportionality theorem. What is it? That is a fact, that is a theorem relating to two similar triangles. What was the theorem? The corresponding sides of two similar triangles are proportional. The corresponding sides of two similar triangles are proportional. Observe the sides 3, 4, 5, 5, 12, 13 and 6, 8, 10. Which sides are proportional? Very clear. 3, 6, 3 by 6, 4 by 8, 5 by 10. All are equal to 1 by 2. Therefore, T1 and T3 are similar. T1 and T3 are similar because their corresponding sides are proportional. The symbol for similarity is this one. And what is the symbol for congruence? In addition to this symbol, there is an equal sign. Okay, that is a symbol for congruence. Then here T1 is similar to T3. Therefore, T1 and T3 are related to each other. Clear? Now let us discuss the last question of this section, that is question number 10. This is not an important question, but a question in your textbook, and also this relation is defined on the set of all human beings. That is why I am going to discuss, but I am not giving you a detailed note of the answer. You just write your note in your own way by listening my explanation. Okay. This relation R is defined on a set of all human beings in a particular town at a particular time given by. First relation is R is equal to ordered per x, y such that x and y work at the same place. X, y are human beings. Two persons work at the same place. The relation connecting them, what is its nature? Is this reflexive, symmetric and transitive? Let us discuss the answer to question number 8 first. That is the relation reflexive? Work at the same place? A person and himself work at the same place, no doubt. Therefore, the relation is reflexive. What about symmetry? X and y work at the same place. Then y and x also work at the same place, no doubt. Therefore, it is symmetric also. What about the transitivity? X and y work at the same office. Suppose in an office they are work in the same office. Then y and x also work at the same office. Therefore, the relation is symmetric. Okay. What about the transitivity? One more person is Z. Z work in this place where y is working. It is clear that x and y work at the same place. Y and z work at the same place. Clearly, x and z also work at the same place. Therefore, the relation is transitive also. Therefore, the relation among human beings working at the same place is reflexive, symmetric and transitive, and hence it is an equivalence relation. Answer to question number B is just same as that of question number A, living the same place. Therefore, that is also a reflexive, symmetric and a transitive relation, that is an equivalence relation. Do it yourself. Do the answer yourself. Okay. Now, answer to question number C. X is exactly 7 cm taller than Y. Can a person exactly 7 cm taller than himself? Never. It's not possible. Therefore, the relation is not reflexive. What about symmetry? Suppose X is exactly 7 cm taller than Y. Is Y exactly 7 cm taller than X? Not possible. Okay, therefore the relation is not symmetric, not reflexive, not symmetric. What about the transitivity? Suppose there are three persons, x, y, z. X is exactly 7 cm taller than y, and y is exactly 7 cm taller than z. What is the relation connecting x and z? X is exactly 14 cm taller than z, not 7 cm. Therefore, whenever xy belongs to R and yz belongs to R, xz is not a member of the relation. Therefore, the relation exactly 7 cm taller than y is not transitive. It is neither reflexive, nor symmetric, nor transitive. And answer to question number D. Here, the relation is wife, an interesting relation. The relation between two persons is wife. Can a person can X be a wife of herself? Never possible. Not possible. Okay, X cannot be a wife of herself, therefore the relation is not reflexive. What about symmetry? Suppose X is wife of Y. Can Y a wife of X? No. When X is wife of Y, Y is husband. Okay, Y is a gentleman. He cannot be a wife of X. Clear? Hence the relation is not symmetric, not reflexive, not symmetric. Now discuss is transitivity. That is something interesting. There are three person X, Y, Z. X is wife of Y. X is wife of Y. What is the basic qualification for a wife? A lady. Okay, X is a lady, and X is wife of Y. Then Y is a gentleman and his husband. Y is husband. Okay, X is wife of Y means X is lady and Y is husband. Then Y is to be Y Z belongs to R. Y is wife of Z. Y is wife of Z means Y is a wife. Y is a wife means this Y must be a lady. Okay, this Y must be a lady. But what is Y? Y is a gentleman. Who is Y? Y is a gentleman. It is not possible to become a lady. Okay, therefore whenever XY belongs to R, then YZ is not a member of R. Whenever XY belongs to R, YZ is not a member of R. Okay, hence the condition is not okay here. Hence the don't bother about the conclusion, and clear the relation is what? Transitive. The relation is neither reflexive nor symmetric but transitive. You can say to your wife in future that, darling, the relation between us is neither reflexive nor symmetric, but keep in mind that the relation between us is transitive. Okay, now answer the question number E. That is the relation is father. Can a person father of himself? No, the relation is not reflexive. Suppose X is father of Y, then can Y a father of X? No, it is not possible, therefore it is not symmetric. And what about the transitivity? Suppose X is father of Y and Y is father of X, then X is grandfather of Z. Okay, X is grandfather of Z, not father. Therefore, the relation is not transitive. Then the relation between father and son is neither reflexive nor symmetric nor transitive. But the relation between wife and husband is neither reflexive nor symmetric but transitive. Today's section is over. Today we discuss all the major questions relating the concept relation in detail. Study it well and write it beautifully in your notebook. In the next part, that is part number 5, we are going to discuss the geometrical explanation of reflexivity and symmetry using the GeoGebra software. Okay, thank you so much for listening my class and have a nice day. Thank you.